All right, so very good day to everyone. I hope this audio finds you, video, sorry, video finds you in good health and in a excellent state of mind. So let's continue from where we had left off. We were discussing about torque and application of the Newton's law. Uh, what we'll do is now move on to the next topic, fine, that is kinetic energy. Fine, kinetic energy. Fine. Okay. Now, whose kinetic energy is this? Well, we know that the kinetic energy of a particle is nothing but how much? If there's a particle over here which has a mass of m and it has a speed of v, then the k is given as equal to how much? Half m multiplied by v square. Fine. Now, what if it is a rigid body over here? Fine. So, this rigid body uh, is nothing but having a collection of many such particles. Fine. So, therefore, over here, this particle may be having a velocity in this direction. This particle may be having a velocity maybe in this direction. Uh, and so, in this way, you have many such particles over here, right? Because the rigid body may be translating, it may also be rotating. Fine. Translation plus rotation, let us say. Fine. So, before we go into the uh, combined translation plus rotation, first we'll just check for rotational objects only. Fine. So over here, we will observe that if there is a object over here, a rigid body, which can rotate about this axis with an angular velocity of omega, fine. And this axis over here is fixed, it doesn't move, fine. Just like your, let's say the ceiling fan, right? The fan is just rotating about the ceiling, fine. So therefore, we want to find out the kinetic energy of this ceiling fan or this object. So what we observe is that every particle over here would be moving in a which kind of a path? A circular path, right? Why? Because all of them have the same value of omega as they keep on rotating over here, right? So if the distance over here is equal to r, the velocity over here is nothing but equal to v. We can write the v value is equal to r omega also, fine. So therefore, the small amount of kinetic energy of this particle, which has a mass of dm, is nothing but how much? Half mass into the square of the speed, correct? And what is the value of this v? Can we write it as r square into omega square? So if this is the small amount of kinetic energy of this particle, then what's the total kinetic energy then? Can we say the total kinetic energy is simply the sum of all the kinetic energy of the particles? Yes. Integral of half dm r square into how much? Omega square. Now omega is going to remain the same for this rigid body, right? So therefore, can we write this as half of integral dm into r square multiplied by omega square? Yes. But what is this quantity over here? Half integral dm r square into omega square. If you observe, this term over here is nothing but the which one? The moment of inertia. So it is half I, the moment of inertia about that axis, into the square of the angular velocity. Fine. So kinetic energy of rotation is nothing but this particular value. Fine. This part is extremely clear, no doubts are there. Yes. Okay. Uh, what do we do now? Let's take some examples from the same. If this is the kinetic energy, then the law of mechanical energy is applicable. For example, suppose that we have over here a rod this way, fine, and this is nothing but the hinge over here, fine, and the mass of the rod is m, length of the rod is l, and this rod, let us say, is being released from where? Being released from rest, let us say, fine. So what would happen as the time passes? As the time passes, this one over here, this rod is going to be making a certain angle, right, with the vertical, right? So we can imagine how the situation will be, right? This way, let's say, this way, fine. This is the vertical, and this angle over here is theta, let's say, fine. And therefore, it will be having an angular velocity omega over here. About what? About the hinge. Every particle of the rod is in pure circular motion about the h point. Suppose you are asked, find out what is the value of this omega. Fine. And so, how do you find out? We can always write that the forces which are doing work on this particular rod, they are the ones that will cause the change in the kinetic energy of the rod. So, what all forces are doing work? Is gravity doing work? Yes. Where is gravity acting on this object? We can say that at the center of the mass, the gravity force is acting. Fine. And what about the hinge reactionary forces? Maybe there is a reaction this way, R vertical this way. Maybe there is a horizontal hinge reaction this way, that is RH. Probably RH is this way. And yeah, now you have to answer this. What is the work that will be done by the force of RV on this object? Now, does RV do any work on this object? No. Why? That point of the rod, which is connected to the hinge, that point is not getting displaced. It's always along with the hinge. So no work is done by the RV force, because even though it may act on the rod, still no displacement is there of that point of application of that force. Similarly is true for RH also. So both are not going to do any work. No work done, and this one also is not going to do any work. Fine. Now there may be an argument that why is there no work which is done and still their forces are acting on it? Well, they will cause acceleration on the center of mass of this rigid body. Fine. Then who is the one who is doing some work? Gravity and gravity only. Now, because of gravity, there is a change in the position of the center of the mass. Earlier, this was the center of the mass. Now, this is the center of the mass. This height over here is how much? Is nothing but equal to h. So, therefore, work done by the force of gravity on center of the mass is nothing but positive work. And since the displacement is downward, therefore, now we'll write that the change in kinetic energy of the rod is nothing but equal to how much? The work done by all forces. Fine. When we say all forces, it's actually the work done by mg plus no others are going to do any work. Fine. So therefore, what can we write over here? We notice that work done by mg is nothing but plus mg multiplied by h, and the final kinetic energy is nothing but half I about the hinge into omega square minus half I about the hinge. What is the initial value of omega of this object? Was it at rest? Therefore, the initial omega is nothing but equal to 0. And final omega is this omega itself. Fine. So therefore, now you have to go back to theory. What is the moment of inertia of this rod about the hinge? This one. Can we say it is 1 by 3 ml square? Yes, let's put that. Half 1 by 3 ml square omega square is nothing but equal to mgh. Okay? That's all. M you can cancel. We also want to write this h in terms of L and theta. So we notice that this distance over here is nothing but equal to L, and this distance over here is L by 2, and this distance over here is also L by 2. So therefore the h is nothing but equal to L by 2 minus of the component of L by 2 this way. Okay? We notice that L by 2 component this way is L by 2 cos of theta. So let us substitute h is this value. Fine. This part is clear. No doubts are there in this particular expression. Fine. Fine. Okay. So now substituting the value over here, L by 2, 1 minus of cos of theta, that is the h value. On the other side, what do you have? Half 1 by 3 L square omega square. You can cancel the L term and the half term, and it leaves us with omega value as equal to how much? Square root of how much? 3g into 1 minus cos of theta divided by L. Right? This part is clear. No doubts are there in this particular example. Yes. All right. So now let's move on further. Fine. Let's move on further on this. Okay. Let's take another case. Suppose that we have over here this is nothing but a pulley, a rough pulley it is. Moment of inertia is I, radius is R. Fine. And there is a string which is wrapped around this pulley. Fine. And on the at the other location there is this point mass over here. Fine. The system is released from rest. Fine. Released from rest. And we want to find out, number one, what is the speed of M after it descends by height h. Okay? After it descends by a certain height of h. Fine. Okay. So therefore, initially again the system is starting from what? Starting from rest only over here. Omega is 0. V value is also equal to 0. Fine. 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 All right. So now let us write that if it has descended by a height of how much? A height of h over here, then its speed over here is nothing but equal to a value which is non-zero, which is v. Fine. And therefore this one also would have attained an omega value. Fine. So therefore let's write the conservation of energy over here. So there are two ways of doing this. One is that we use the energy conservation, or second is that we use the work energy theorem. Fine. So let's do this using work energy theorem. Fine. That also will give. Both are the same. So therefore, we can write that the change in the kinetic energy of the system is nothing but equal to the work done by whom? By all the forces. There are only two forces. One is the work which is being done by mg, or the mg force. The other work is nothing but the tension. But there is no net work done by the force of tension. Over here, it will do some positive work on the pulley, and over here, it will do equal and opposite work on the point mass. So, as a whole, the force of tension will never do any amount of work. Fine, fine. So, therefore, this part over here is simply equal to 0. And since the descent over here is by a height of h, directly you can write plus mgh itself. Now, what is the final kinetic energy of the system? Now, because the pulley is rotating, it has half I omega square. Because particle has this much of speed, it has half mv square. So let's write over here final kinetic energy minus the initial kinetic energy. Final kinetic energy is nothing but half of I omega square plus half of m into v square, because both of them have kinetic energy. Initial kinetic energy is 0 for both of them. The problem here is we need to find the speed v, but omega is not known to us. What do you do in such case? Yes, we will have to go to a constraint. Fine. We will recall a constraint that we did earlier. We said A is R alpha, or no slip of the string over the pulley. Fine. The same way, to carefully look, if this point over here it has a speed of v, then every point on the string must have the same velocity along the string, right? And this point over here, which is connected to the pulley, right? This point must also have the same velocity of v. Only then there can be no slip over here between these 2 points, P and Q. Otherwise, there'll be slip between the string and the pulley here. But we know that the point P on the pulley has a velocity of how much? R times of omega. This is the V of the point P. Fine. So therefore, let us take this and substitute over here. We'll replace which one? Let's replace the omega over here, and we're done. So therefore, this we can write half I omega is V by R plus half mv square is uh, is mgh. Fine, fine. So therefore, V you can pull outside, and inside we would be having, what all we have? I by R square plus m. On this side you have mgh, and that's it. So the value of V, square root of mgh divided by m plus I by R square. Fine. This part is clear to us. No doubts are there in this particular example. Fine. All right. Now let's take up another example. Life is full of examples. Fine. Full of examples life is. This example we have taken. Let's take another. Okay. What do you want to take? Let's take a rod case, which is rotating. Fine. Okay. Suppose that we have over here the axis of rotation this way, And this is a rod over here. Fine, fine. And this rod has a mass of m, it has a length of l. The angle over here is theta. This rod is rotating about this axis in this way. Fine. With what angular velocity? With omega. Fine. We want to find out what is the kinetic energy of this rotation. Fine. So the kinetic energy of rotation, we can always write it as half I of the system about the axis times omega of the system about the same axis. You have to you have to recall what is the moment of inertia of the system about this axis. You'll go back to the first or second lecture on this moment of inertia. A rod which is inclined at an angle of theta to the axis has a moment of inertia of how much? 1 by 12 ml square sine square theta, correct? That's all. Our problem is done. 1 by 24 ml square sine square theta omega square. Towards the end of this chapter, we'll also find out the value of omega for this rod. The moment you give or fix the theta value, omega is a function of that theta itself. That we'll do in the towards the end. Fine.